Good afternoon, class. We are looking at pre-calculus practice test number 2, module 2, covering chapters 3 and 4. Here's chapter 3, polynomial and rational functions. Second part, part 2. Let f of x be equal to x over x minus 2. Sketch the graph of f using technology to determine whether f is one-to-one function. We have seen how to graph rational functions. The assumption is at this point, we know how to do them. So for a quick check, so we graph it. Again, the assumption is everybody knows how to do that. Yes, it is a one-to-one function because it passes HLT, horizontal line test. Look at the vertical asymptote. Look at the horizontal asymptote. The vertical asymptote, x equals 2. The horizontal asymptote, y equals 1, because they have the same degree. If f is a one-to-one function, find f inverse and sketch the graph of f inverse. To find that, we go back here and we change f of x to y because it makes it easier to work with. We do the cross product. But before we do that, we can change x and y. You can do them in any order. You can do the cross product and change x to y afterwards, or you can change it now. So let's actually change it beforehand. So y becomes x, x becomes y, and now you do the cross product. Makes no difference, as I mentioned. So when you do the cross product, you get x times y, x times -2 equals y. And since you want to solve for y, we are going to move things around. When I move the y, becomes negative y. We move the -2x, becomes positive 2x. On the left side, we can take out the y as a common factor. And now we're going to divide both sides by x minus 1. And so y, or in this case, f inverse, is 2x over x minus 1. Now, we graph it. What do we notice? Well, look at the horizontal asymptote here is y equals 1. The vertical asymptote here is x equals 1. Look at the vertical asymptote x equals 2, horizontal asymptote y equals 2 here. Well, so VAs versus HAs. If we look at the domain for this function, you said x minus 2 equal to 0 and you excluded. That means from negative infinity to 2, union 2 to infinity. And if the domain of f is this, the range of f inverse is the same thing. Range of f inverse is the same thing, everybody. But what about range of f inverse? X can't be 1, negative infinity to 2, union 2 to infinity. Now this one, domain of f inverse is the same as range of f inverse. Range of f is the same as domain of f. So that's pretty straightforward, everybody. Solve the following inequality, graph the solution set, write it in interval notation, x squared minus 3x minus 18 over x plus 2 greater than or equal to 0. The technique is you make sure that one side is 0. So if by any chance you have anything on the right or left, you bring them all to the same side. Then you do the factoring. This will be You're looking for two numbers. The product is -18. The sum is -3, x plus 3, x minus 6. Then you set the top equal to 0, the bottom equal to 0, and those are the points that create sub-intervals. So if you set the top equal to 0, you get -3 here, +6 here. The bottom gives you -2. So you have a number line going from negative to positive infinity, and those numbers, you put them in order. So again, -3, +6, -2. So you put -3, -2, 6. Notice the top is 0. Again, let's just write it. When you set the top equal to 0, x equals -3, 6. That's why we have 0 here. However, when the denominator is 0, that is undefined. UD short for undefined. Now what happens? You just pick up a test point. And by the way, they will alternate, because if you look at the factor form, this has degree 1, this has degree 1, this has degree 1, in essence, odd degree. So if you come up with one of them, the rest of them alternate. The easiest one between -2 and 6. By the way, test point TPs, this would be like -4 here, would be -2.5 here. 0 is the best point, and let's say 7 here. I'm going to just try 0, and I'm going to show you how that works. If I put the 0 here, it may be easier to put it into this one, because everything goes to 0. -18 over 2 is -9. So if plug in 0, you get negative. They will alternate. That means positive, positive, negative. Or you can actually check, put -4. Now, put the -4 into the factored format, it's easier. Here's the reason. -4 here, +3 is negative. -6 is negative. Negative times negative is positive. Put the -4 here is negative. Positive over negative makes it negative. So you can do that. Now, how do we do that? We go back to this, and it says greater than or equal to 0. So we want this vicinity and this vicinity. That means from here to here, union here to here. How do we write them? At -3, 0 equality is fine. But at -2 is undefined. So -3 takes bracket, -2 takes parentheses. Union. 6 is 0, so it takes bracket to infinity. And by the way, infinity or negative infinity are both concepts. They will always take parentheses. What about the number line? We are going to locate those numbers. So for example, from 6 all the way to infinity, and 6 is included, you can put a bracket or solid point. Then between -2 and -3, -3 is included. Yes, -2 is not. So that's how you graph this. The end behavior of a polynomial function is the behavior of the graph of f of x as x approaches positive infinity or negative infinity. The degree and the leading coefficient of a polynomial function determine the end behavior of the graph. F of x is a sub n, x to the power of n, plus a sub n minus 1, x to the power of n minus 1, all the way to a sub 0. And what the end behavior says that ultimately the graph will look like this piece, y equals a sub n, x to the power of n, which is known as the leading term. So if the degree is even and leading coefficient is positive, this number is positive, then f of x goes to infinity, x goes to minus infinity, f of x goes to plus positive infinity, also positive infinity, meaning ultimately, look at y equals x squared, the first and the second quadrant. Those are the end behavior. However, if this leading coefficient is negative, for example, f of x equals minus x squared, it opens down. That's the idea. F of x approaches negative infinity, when x approaches negative infinity, and f of x approaches negative infinity as x approaches positive infinity. Doesn't matter. In this case, both cases, y goes to infinity, whether we go to negative or positive infinity. In this one, the other way around. However, if the degree is odd, such as y or f of x equals x cubed, if x goes to negative infinity, so does y. If x goes to positive infinity, so does y, as long as a sub n is positive, like y equals x cubed. If it's minus x cubed, so a sub n is negative, then it's the other way around. So this was first and third quadrant. This is the second and fourth quadrant. That means if x goes to negative infinity, y, by f of x, we mean the y coordinate in essence, goes to positive infinity. And if x goes to positive infinity, f of x goes to negative infinity. This is known as the end behavior of the function. Also, we have a theorem about behavior near a zero or x-intercept and multiplicity of 0 x minus c to the power of m. The multiplicity is m, meaning x minus c times itself. How many times? M times. If m is odd, f of x crosses the x-axis at its 0, c comma 0. However, if m is even, it can't cross the x-axis at that point. So if you look at this one, for example, it crosses. In this case, 2, multiplicity 2. In this case, multiplicity 3, it can't cross, okay? The higher the multiplicity, the flatter the curve is at the 0. The sum of the multiplicities is the degree of the polynomial function. Number of zeros theorem. A function defined by a polynomial of degree n has at most n distinct or unique complex zeros. Again, single zero, that means multiplicity 1, 0 with multiplicity 2, and multiplicity 3. Graph the following polynomial using the end behavior and behavior near an x-intercept, where f of x is given as x cubed minus 5x squared minus x plus 5. Well, let's find the zeros. And one way to do it, we can do it by factoring. If we put these two together, we can take out x squared, and it becomes x squared times x minus 5. And the last two, just take out negative 1. And now they have a common factor of x minus 5. If you take it out, you get x squared minus 1. And as you know, x squared minus 1 is x plus 1, x minus 1. So it's completely factored out. So we have the intercepts 5, 0, negative 1, 0, positive 1, 0, and all of them have exponent 1, multiplicity 1. All have m, multiplicity 1. What is the leading term? X cubed. That means ultimately looks like x cubed. Okay, so those are the 3 zeros. By the way, if you go to the original one, it's easier to see. If you set x equal to 0, you get 5. So 0, 5 is the y-intercept. And as I mentioned, the leading term is x cubed. The end behavior, n is 3, it's odd, and a sub n equals 1 is positive. So the first and the third quadrant, everybody. So as x goes to negative infinity, so does y or f of x. As x goes to infinity, so does y or f of x. So it looks like this, and it crosses. By the way, because the multiplicity is odd, it crosses. It crosses. This one has to come back up and hit those. That's the way it looks like. And this is the, in essence, a better graph, everybody, with a little bit more details. Now graph the following polynomial using the end behavior and behavior near an x-intercept. G of x is x minus 2 quantity squared times 2x plus 3. Well, we have the x-intercept 2, comma 0, and negative 3 halves, comma 0. This has multiplicity 2, this has multiplicity 1. So x-intercept, we have 2, 0, and negative 3 halves 0. Again, this has multiplicity 2, this has multiplicity 1. So what does it mean? Well, let's put those 2 points. This has multiplicity 2. That means it can't cross. So the way we do a double arrow, meaning when it hits it, it can't cross. Whether it comes from up, has to go back up, or from down, goes back down. That's why we use this double arrow. Now, what about the y-intercept? What is y-intercept? Set x equal to 0. If x is equal to 0, what you have is negative 2 squared times 3, which makes it 4, times 3, which makes it 12. And so we have 0, 12. Now, do you have to multiply them out? No, I'm really interested in the first term. I hope you see that this is x squared times 2x is 2x cubed plus the rest. I'm assuming everybody can come up with that. What I'm interested in this is this. Why is that? Because here's the leading term. N is 3, which is odd, and a sub n is 2, which is positive, and therefore it acts like x cubed, meaning as x goes to negative infinity, f of x goes to negative infinity. As x goes to positive infinity, f of x goes to positive infinity. And so it looks like this. Now, as it hits this one, so it comes down, but it can't cross and goes like that. Now, as far as where it ends, this is the max. It here, we may not know, and we will learn about that in calculus. But nevertheless, that's what's happening. And this is perhaps a better graph showing you a little bit more details. What is the least possible degree of the polynomial? Write an equation for the polynomial graph. So first and foremost, let's go with some theorems. Turning points, where the graph of a function changes from increasing to decreasing. So decreasing, increasing, or to decreasing or vice. This is from decreasing to increasing. This is increasing to decreasing. So for example, 1, 2, 3, the turning points or the local extreme or local max, local mean. The number of turning points of the graph of a polynomial function of degree n larger than or equal to 1 is at most n minus 1. The number of the local maximum point, highest point or peak in an interval. Function values, in an interval, function values at these points are called local maxima. Local minimum point, lowest point or valley in an interval function values at these points are called local minimum. So local mean, local max, local mean. Plural of extremum includes all local maximum. By the way, this one happened to be an absolute minimum as well. Okay. So what is the least possible degree? 1, 2, 3. So it must be 4. Why is that? Because we have 3 terms or 3 peaks and valleys, 3 extrema. Write an equation. Well, this one is -3 and it crosses. So multiplicity 1. This is -2 and it crosses multiplicity 1. This is +1 and it doesn't cross. So we have the multiplicity. So f of x is some number a. This one would be x plus 3. This one would be x plus 2. And this one would be x minus 1 squared. Okay, so f of x is a times x plus 3 times x plus 2 times x minus 1 quantity squared. All right, we seem to be in good shape. What's missing in action is a, and we need one more point. Clearly, we can see the y-intercept here, having coordinates 0, 3. If I replace the x with 0, I replace f of x, which is the y coordinate, with 3. So this is 0 plus 3 is 3, 0 plus 2 is 2, 0 minus 1 is minus 1. Minus 1 squared is 1, so we have 1 equals to a, which makes a 1/2. F of x becomes 1/2, parentheses x plus 3 times x plus 2 times x minus 1 quantity squared. Find the degree, leading coefficient, and the maximum number of real zeros of the polynomial f of x equals 2 plus 3x to the power of 6 plus 4x to the power of 7 minus 6. Also describe the end behavior or long-run behavior. First and foremost, we should put this in descending order, starting with 4x to the power of 7. Polynomial function of degree n in the variable x. P of x is a sub n x to the power of n all the way to a sub 0, where each a sub I is real. A sub n can't be 0, and n is a whole number, 0, 1, 2, 3 to infinity. A sub n is called the leading coefficient. A sub n x to the power of n is called the leading or dominating term. A sub 0 is called the constant term. So putting it in descending order results in 4x to the power of 7 plus 3x to the power of 6 minus 6x plus 2. And clearly, this guy is the leading term. So the degree is 7. The leading coefficient is 4. Degree 7. Leading coefficient is positive 4. Okay, so we got the degree. We got the leading coefficient. Maximum number of real zeros is the degree. So maximum number of real zeros must be 7. Describe the end behavior. Well, leading term is 4x to the power of 7. N is 7, which is odd. A sub n is 4, which is positive. Therefore, it must behave like x cubed, meaning as x goes to negative infinity, so does y, meaning f of x goes to negative infinity. As x goes to positive infinity, so does y. That means f of x goes to positive infinity. Okay. Use number of zeros theorem and Descartes' rule of sign to discuss real zeros of f of x. Fill up the table where f of x is given as 3x to the power of 7 minus 4x to the power of 4 plus 3x cubed plus 2x squared minus x minus 3. So we have positive zeros, negative zeros, imaginary zeros, and the total. So that's what we are going to discuss. So first and foremost, notice this is in descending order. So we don't have to worry about that. Otherwise, I highly recommend you put it in descending order. What is this? The leading term is 3x to the power of 7. So 3 is positive and n is 7. So max would be 7. So use the number of zero theorem to discuss real zeros. So maximum number of zeros is 7. Therefore, the total must be 7. Also, let's look at some theorems. Descartes' rule of sign determine the number of positive and negative zeros. Let f of x be the polynomial function. F of x is a sub n x to the power of n all the way to a sub 0. With terms in descending powers of x, as we have it here. A, the number of positive real zeros either equals the number of variation in sign occurring in the coefficient of p of x or is less than the number of variation by a positive even integer. Part B, the number of negative real zeros either equals the number of variation in sign occurring in the coefficient of p of minus x or is less than the number of variation by a positive even integer. So I want to stick with part A, then we'll discuss part B in a moment. So part A says the number of positive real zeros either equals the number of variation in sign occurring in the coefficient of p of x or is less than that. So what do we have here? This is positive, negative, positive, positive, negative, negative. So those are the signs. So the number of positive real zeros either equals the number of variations. So as we change from this to this, there is a variation. From here to here, there's a variation. Here to here, there is no variation, everybody. Here to here, there is a variation. Here to here, there is no variation. So we have 1, 2, 3 variations. So positive real zeros. According to part A, positive would be 3. Maximum would be 3. Now, part B says find f, in this case, p of minus x, or in this case, f of minus x. It says the number of negative real zeros either equals the number of variations of sign occurring in the coefficient of p of minus x, or is less than the number of variation by a positive even. So first, let's calculate f of minus x. So let's see, if I replace the x with negative, this becomes minus, so minus 3x to the power of 7. This one doesn't change, so minus 4x to the power of 4. This one changes to negative. This one, because the exponent is 2, doesn't change. And so plus 2x squared. This one changes to minus minus x plus x, then this one doesn't change. So what signs do we have? Negative, 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 positive, positive, negative. So those are the signs. What do we notice? From here to here, no change. No change. From here to here, there is a change. Here to here, no change. Here to here, there is a change. So there are 1 and 2 changes in sign. That means negative real zeros must be 2. If the total is 7, we have 3 positive, 2 negative, the rest of them must be imaginary. A plus BI. So 7 minus 3 plus 2, which is 5, makes it 2. The second part of that says, okay, the number of positive real zeros either equals to the number of variations. We got 3. or is less than the number of variation by a positive even integer. So it's either 3 or we go down by 2. If we go down by 2, this becomes 1. This becomes 0. So if this is 1, this is 0, they add up to 1. This must be 6 because the total can't change, everybody. Now this can't go any down, okay? So we can have 3, all possibilities. We can still have 3, and this goes down to 0. So if this goes down to 0, then this must be 4, total of 7. Or if this one goes to 1, this goes down to 1, but this remains as 2, 1 and 2, 3, this must be 4. The total of 7 does not change, everybody. And here's what's important. Imaginary zeros are in the form of a plus minus bi, must occur in pairs, 2, 6, 4, 4. So that's how you figure out the sign, positive or negative. What is the least possible degree of the polynomial? 1, 2, 3, 4 terms, so must be 5. There are 4 terms for extrema. This is a local mean, local max, local mean, local max. They are all local. This one, because there is no other point, having a smaller y coordinate is also considered an absolute max. All right, they want us to write an equation for the polynomial. So let's put the x-intercepts. And so we notice this is -4. So x plus 4. This is -1, x plus 1. This is positive 2, x minus 2. This is positive 4, x minus 4. So this crosses, this crosses, this crosses. This one doesn't cross. This one is the only one with an even multiplicity. For example, 2. So what is that equal to? We write for this one x plus 4 times x plus 1 times x minus 2 times x minus 4 squared. And then we put something in front of it like a. So everything is there except a. How do you find it? Pick up another point. An easy point would be the y-intercept, which is located at 0, 2. So replace the x with 0 and y or f of x with 2. This is 16. So 4 cancels out. The 2 gives us 2. 2 times -2, -4 times 16, -64. So that means 1 is equal to -64a. A must be 1 over -64 or -1 over 64. Replace this. And the final answer is f of x was -1 over 64 times x plus 4 times x plus 1 times x minus 2 times x minus 4 squared.